Hello everyone. Welcome back to my course Aerospace Engineering, Avionics and Aerospace Systems. In this video, we will talk about the general description of fuel systems. Also, I would be thankful if you give me feedback about this course to make it better and more useful for you. Please write down your thoughts in the comment section or reach out to me via the email provided in my profile. The fuel system in an aircraft is one of the most vital components ensuring safe and reliable operation. Its primary function is to store and deliver the correct quantity and quality of fuel to the engines under all operating conditions, whether the aircraft is on the ground, in climb, cruising at high altitude, or descending for landing. The fuel system must be capable of maintaining consistent pressure, temperature, and flow rate, while also adapting to changes in aircraft attitude, engine demands, and atmospheric conditions. Beyond simple fuel delivery, the system plays a critical role in overall aircraft performance. It must prevent vapor lock, fuel starvation, and contamination, while also supporting auxiliary operations such as fuel jettisoning, cross-feed between tanks, and fuel transfer for weight and balance optimization. The fuel system must meet strict regulatory standards for safety, reliability, and environmental impact, making its design and integration a sophisticated engineering challenge. Role and importance of the fuel system in aircraft operation. The fuel system's importance lies not just in powering the engine, but also in enabling aircraft to meet performance goals such as range, endurance, and payload capacity. The system has to work flawlessly at varying altitudes, where pressure and temperature differ significantly, and must continue to deliver fuel under conditions of turbulence, icing, or rapid changes in power demand. In multi-engine aircraft, redundancy and cross-feed capabilities are critical to maintain operation, even if one part of the system fails. In high-performance or commercial jets, integration with avionics and automated flight systems ensures optimized fuel consumption, enhancing efficiency and reducing emissions. Safety is paramount in aviation, and fuel system failures have historically been major contributors to incidents and accidents. Hence, modern systems incorporate multiple fail-safes, pressure relief valves, contamination monitoring, and real-time diagnostics to detect irregularities early. Overview of basic fuel system layout and flow path. Although the specific layout of a fuel system can vary significantly depending on the type and size of the aircraft, there are several common components and flow sequences that define a standard architecture. Fuel is typically stored in tanks that are integrated into the wings, fuselage, or sometimes the empennage, tail section. From the tanks, fuel is drawn through a series of lines by boost pumps, either electric or engine-driven. These pumps ensure fuel reaches the engines even under high demand or when gravity feed is insufficient. The fuel then passes through filters that remove water and particulate contamination before reaching the engine-driven fuel pump. This pump raises the fuel pressure to meet engine requirements. From there, fuel flows through the Fuel Control Unit, FCU, where it is metered based on throttle inputs, altitude, and engine load. Finally, the fuel is injected into the combustion chamber for ignition. In more complex aircraft, additional components such as fuel transfer pumps, selector valves, crossfeed valves, and fuel heaters are included to manage fuel routing, balancing, and thermal conditions. Venting systems are used to maintain pressure equilibrium in the tanks, while sensors monitor fuel quantity, temperature, and flow rate. Types of aviation fuel. There are several types of aviation fuel in use, each designed for specific engine types and operational environments. Avigas, or aviation gasoline, is primarily used in piston engine aircraft. It has a high octane rating to resist engine knocking under compression. The most common grade is Avigas 100LL, where LL denotes low lead. Despite this, it still contains tetraethyl lead, a toxic additive necessary for detonation resistance in high-performance piston engines. Jet fuels are used in turbine-powered aircraft, including turbojets, turbofans, and turboprops. Jet A is a kerosene-based fuel commonly used in the United States. It has a high flash point and relatively low volatility, making it safer to handle. However, its freezing point of approximately minus 40 degrees Celsius limits its use in extremely cold conditions. Jet A1 is an internationally used variant with a lower freezing point of around minus 47 degrees Celsius. This makes it more suitable for long-haul, high-altitude flights where outside air temperatures can drop significantly. Jet B is a blend of kerosene and gasoline, designed for extremely cold environments such as the Arctic. It has a lower flash point and higher volatility than Jet A or Jet A1, allowing for easier ignition at low temperatures, but posing greater fire risk during handling. Jet B is less commonly used and is typically reserved for military or specialized operations. Fuel properties, grades, additives, and impact on system design. The properties of aviation fuel directly influence fuel system design. Important properties include volatility, density, viscosity, flash point, and freezing point. Each of these characteristics affects how the fuel flows, ignites, and is stored. Volatility determines how easily a fuel vaporizes, which is critical for combustion and startup, especially in cold conditions. High volatility fuels are easier to ignite but are more prone to vapor lock. Conversely, low volatility fuels like Jet A require more robust pressurization and heating systems. Density affects the weight of fuel carried on board and is crucial in calculating range and fuel burn. Since jet fuel is sold by volume but used based on mass flow, accurate density measurement is essential. Viscosity impacts how fuel flows through pumps and lines. In colder temperatures, viscosity increases, which can hinder flow. Fuel heaters or additives may be necessary in such cases. The flash point is the temperature at which fuel vapors can ignite. Jet fuels have higher flash points than gasoline, making them safer for handling. The freezing point defines the temperature below which fuel may solidify or wax, potentially blocking filters or lines. This is why Jet A1 and Jet B are used in cold weather operations. Additives are often mixed into fuel to enhance performance and safety. Anti-icing additives such as fuel system icing inhibitor (FSCOI) prevent ice crystals from forming in the fuel lines. Corrosion inhibitors extend the life of metallic components. Static dissipators prevent buildup of static electricity, which could lead to sparks. Biocides may be used to prevent microbial growth in tanks, particularly in humid or tropical environments. All these fuel characteristics dictate material selection for tanks and piping, filter sizing, pressure ratings of pumps, and sensor design. The entire fuel system must be engineered to operate effectively across a broad range of operational conditions. System integration with engine performance and aircraft operations. In modern aircraft, the fuel system is not a standalone subsystem, but is tightly integrated with the engine control and flight management systems. The Fuel Control Unit, FCU, plays a central role in metering fuel flow to maintain the desired thrust output. It adjusts fuel delivery based on pilot inputs, engine speed, altitude, air temperature, and load demands. The fuel system also interfaces with avionics to provide real-time data on fuel quantity, temperature, pressure, and consumption rates. This information is essential for flight planning and in-flight decision-making. For example, the Flight Management System (FMS) uses fuel flow data to calculate optimal cruising altitudes, predict arrival fuel, and suggest diversions if necessary. Weight and balance considerations are another key area of integration. Fuel distribution can affect an aircraft's center of gravity, CG, and in some cases, fuel is transferred between tanks during flight to maintain optimal CG. In long-range aircraft, this active balancing improves aerodynamic efficiency and ensures compliance with regulatory limits. Safety features like automatic shut-off valves, fire suppression systems, and backup fuel paths ensure continued operation during emergencies. Redundancy is built into most systems to allow continued flight, even if a pump fails or a tank becomes unusable. Ultimately, the fuel system is designed not only to support the engine's operation, but to contribute to the broader goals of fuel efficiency, performance optimization, safety, and regulatory compliance. Its successful operation is essential for modern aviation. Okay guys, now let's have a little quiz. The quiz consists of 3 questions. I'll give you 10 seconds for each one, and then I'll show you the correct answer. Let's start with the first question. Question 1. What is the primary role of the fuel system in an aircraft? The correct answer is to store and deliver the correct quantity and quality of fuel to the engines under all operating conditions. Question 2. Which type of aviation fuel is primarily used in piston engine aircraft and contains tetraethyl lead? The correct answer is avigas. Question 3. Why is fuel crossfeed capability important in multi-engine aircraft? The correct answer is it maintains operation even if one part of the fuel system fails. Unlock the world of aerospace engineering with 2 of my other expertly designed courses. In Aerospace Engineering, Basics of Aviation Engines, you'll explore the different types of aerospace engines and how they perform, giving you a strong foundation in propulsion systems that power modern aircraft. Then, take your knowledge to new heights with Aerospace Engineering, Aerodynamics and Structures, where you'll dive into the design and performance of aerospace structures and their aerodynamic behavior. Whether you're a student, aspiring engineer, or aviation enthusiast, these courses will equip you with essential knowledge to understand and contribute to the future of aviation. Join hundreds of learners and start building your aerospace journey today. Thank you guys for watching this video. If you have any questions about this lesson, feel free to ask me in the comment section. I will answer as soon as possible. We can continue to the next lesson and learn about fuel storage and distribution. See you in the next video. Bye.